Okay, hello. Today we'll be solving problem 2.16 out of Griffiths, and we have this figure 2.26 here on the right. So we have a long coaxial cable carrying a uniform volume charge density rho on the inner cylinder with radius A that you can see here. And then we have a uniform surface charge density on the outer shell with radius B. And we have that the outer shell is negatively charged and the inner cylinder is positively charged, since they're equal and opposite. And so the problem wants us to find the electric field in each of the three regions: inside the inner cylinder, between the two cylinders, and outside the entire configuration of the entire wire. And then we're going to plot the electric field as a function of S. So let's begin by writing Gauss's law, and we're going to have from Gauss's law that the surface integral of the electric flux is equal to 1 over epsilon naught times the enclosed charge, total enclosed charge. Okay, and so what we're going to do now is write it down as we speak. So place a Gaussian surface as a coaxial cylinder with radius S less than A inside the innermost cylinder and with length L. So what we're talking about here is a coaxial cylinder inside of this inner solid charge density cylinder. Okay. So if we take a look at this configuration, we're going to see that the electric field of each charge element points radially outward, and all the off-radial directions, say from this charge as they emanate outward, are canceled by adjacent charge elements due to the symmetry of the problem. So what we're going to see is that the electric field vector is purely radially outward along this length of the cylinder, and then the electric field in the direction of these ends of the cylinder is going to be 0, so there will be no z component. Then if we take a look at the unit normal vector for the area, it's going to be radially outward, and for these ends it's going to be outward through these ends. So we're going to take Gauss's law, and all we're going to do is decompose it into two portions. We're going to talk about the cylinder ends as well as the cylinder length. So for the cylinder length, we said it was radially outward, and since also the unit normal vector is radially outward, we simplify this dot product into a scalar product because they are co-aligned, right? And so this we now have the electric field magnitude. And for the cylinder ends, we said there was no radial direction aligned with the unit normal outward. Sorry, there was no electric field in the z direction along which this area element is. So we're going to have a surface integral value of 0 here. Okay, so let's just evaluate these two surface integrals. So we have 0 contribution from the ends, and from the cylinder length, this electric field is constant all the way around. So we're going to factor it out of the integral and then just integrate over this cylinder length. And so that gives us an area of 2 pi SL, which is the circumference times the length, right? And so for this enclosed charge, we're going to have a constant charge density times our volume of the enclosed charge. And so we have to be careful not to integrate this entire rod here. We're only integrating within our Gaussian surface. And so this volume is here pi s squared L. And this s is our radius of our circle, base times height, right? And so now we're just going to rearrange and solve for the electric field vector 2 epsilon naught, right? And we know it's in this cylindrical radial direction, so we're going to write it as such. and we're going to box our answer. Outside borders. Okay, moving on to the next domain, which is between the two cylinders. This time, we're going to place our Gaussian surface also as a coaxial cylinder, but instead of radius within A, it's going to be between A and B, and not within the innermost cylinder, right? And it's going to have length L, like once more. Okay, and so by the same argument, the electric field vector is radially outward and 0 in the z direction. So we're going to decompose our surface integral in the same way. We're going to have 0 through these ends. E is going to be constant, and we're integrating over the enclosed charge density, which now we're going to have, right, this same result, but rather than integrating all the way to S, there is no charge out between A and S, so it goes only up to A. Okay, so our enclosed charge is going to have this volume, which is this innermost cylinder, and our Gaussian surface area stays the same because this is a variable S with our new within our new domain. Okay, so we're going to solve for this electric field vector, and just from the, I just copied it from above, but what we're going to solve is from the prior expression. And so what we have is rho A squared over 2s epsilon naught in this outward radial direction. All right, now for our last domain, where we want to plot outside of this entire charge configuration, copy over again, once more Gauss's law, and we are going to place our Gaussian surface outside the configuration, right? So now S is greater than B, right? And it has width length L. Okay, but now what we know is from what was given in our problem is this inner cylinder has charge plus Q, total plus Q, and the outer has minus Q. So our enclosed charge is now 0. So decomposing as we did before, we have 0 through the ends. Electric field is radially outward, but this left-hand side here is 0. So what we're going to find is our electric field vector is also 0. And so let's box our answer. And then we're going to move over to our plotting software, where we're going to demonstrate this electric field as a function of S. Okay, so now that we have the electric field within this radius A, between radii A and B, and outside of B, what I've done is rewritten these for within A, between A and B, and outside of B, it's just 0. So what we're going to do now is have the S coordinate serve as the X direction, and here I have plotted A as it's an arbitrary variable, but we're going to assign it as 2, and we're just plotting X equals A. So this is the A radial position, and the B radial position, very similarly, is out here, okay? And so now we're going to change these equations a little bit, just rewrite them in terms of constants and whatnot, and the X direction. So for this first equation, we see rho S over 2 epsilon naught. We see rho over 2 epsilon naught is just a constant, so we're going to rewrite that in this way, and S is going to become X. So at the end of the day, what we have is E equals constant, and we're going to write that as C, X, okay? So let's write this first equation. What we're going to have is Y equals C, this constant, rho over 2 epsilon naught, times the S direction, or X, in this plot, okay? But what we know is that this is only valid between 0, the very center line of the cylinder, and this outer radius A. So as we mentioned before, the electric field rises linearly within this uniform density, and it goes to this maximum value here. Okay, now for between A and B, we have a very similar constant with this equation. So rho over 2 epsilon naught times a squared divided by s. So we're going to rewrite it in that fashion. Hopefully you can see that clearly. So we just have factored out the same constant here as the above equation, and we now have it as c constant times a squared divided by x. There we go. Okay, and so now we're going to write in this second domain, the second equation. So y, which is the electric field here, this vertical axis, is c a squared over x. Oh, sorry about that. Over x. Okay, and we know that this is only valid between a and b. Okay, and so we have this linear rise, then this inverse over power 1 s distance fall off, almost like it's a line charge, and that's a well-known result. And then finally, we have electric field equals 0 outside of the two cylindrical charges. And so we're going to have b outside greater than x. Okay, and so we have this piecewise defined function where it rises linearly, the electric field falls over 1 over r, 1 over s, between the cylinders, and then falls to 0 everywhere outside the cylinder. Okay, thank you.